Hi everyone, I hope you're all enjoying a couple days off and staying out of this cold weather and staying safe. Anyways, I do want to give you a bit of an assignment and have you work through the material we're going to cover for our second lab on stats and data analysis. Much of this is stuff that you can do on your own with your own computer. I highly encourage you, if you are inclined to work with someone else in the class, you are more than welcome to do this for today's assignment. That's encouraged. It might help you understand some of the things a little bit better and work through some of the struggles together. So I'm going to go over what we'll be doing. I'll give you some examples, so it should hopefully make your assignment for this lab run a bit more seamlessly. But the reason that we're covering stats is something that you will see pop up as you go on in your study of the sciences. It's certainly an important field for all areas of science and allows us to interpret our data in a more meaningful way. So think for a second, just pause the video and take a minute to analyze this graph. Think a little bit about what it relays, what information does it convey, and how could it be improved? What do you think? If you said, if you struggled to come up with answers for this, I don't blame you. This graph is not it's not well made. It's very hard to come up with a takeaway. You know, given the title, that it has something to do with scores, but what scores? Scores for what? For a baseball game? For an exam? It could be anything. We have no idea what these numbers on our x-axis convey, nor do we have any idea what the numbers on the y-axis convey. Some of you may have noted that we're dealing with a 3D graph. Excel has all sorts of fun types of graphs, but these 3D graphs make it sort of difficult to figure out exactly where the bars fall on our scale. So oftentimes it's best to put together just a simple graph and not use some of these flashy features. If we move ahead to the next slide, now take a minute to look at this graph and see what you come away with. Pause the video if you want to just take a minute here. So looking at this graph, there's a lot more information. And believe it or not, this graph here was created with the very same data set as the last graph that you saw. But here the title is very well developed. We know that we're comparing exam scores of morning and afternoon lab sections. We see bars for both the morning lab and the afternoon lab. We're differentiating males and females. That's what the two colors represent. And then on our y-axis, we have the exam scores that we're interested in. So we can see a couple takeaways here. In the morning lab, didn't quite do as well as the afternoon lab in terms of scores. Sorry guys, if you're in the morning lab. No real difference in males and females in the morning lab, but in the afternoon lab, females seem to do quite a bit better than males, or a little bit better at least. So good job, ladies. So this graph has a lot more information. Going back to that last graph, we have maybe individual scores for each of the students now that we know a little more of our story. But what we did with that data in the second graph is we just pared the information down to the averages of those scores. So it's a lot easier to see what's going on. So now think a little bit about how stats might help us interpret this data. Well, the benefit of stats is it allows us to assess whether there really are statistically significant differences between exam scores. Is there a true difference or a statistically significant difference between the afternoon lab scores and the morning lab scores. Or maybe there isn't a statistically significant difference there. Stats can help us to answer these types of questions. So many of us probably know at least a baseline definition of hypothesis. This is a term that's very familiar to us in the sciences. We're going to differentiate, though, a couple of different types of hypotheses, and this will be important for you to understand. First of all is the null hypothesis. Under this hypothesis, we're saying that there is no difference between means or averages of two groups. So null meaning no. So there's no difference between two groups. So there is no statistically significant difference between the exam scores in morning and afternoon labs. That would be the null hypothesis. And that's denoted in the notation you see here. H sub O is where our two means, mean of population 1 and population 2, are equal to one another. Our alternative hypothesis, however, might be kind of what we expect to happen or expect to find. So here we're saying that, hey, yes, there is a significant difference between the means of two or more groups. So there's a couple ways we can portray that. We can simply say our first alternative hypothesis is simply that the means are not equal to one another. We could also hypothesize that the mean of population 1 is greater than that of 2, or vice versa, the mean of population 1 is less than the mean of population 2. In the sciences, when we frame our hypothesis, it's always a good idea to use the null hypothesis. So your initial hypothesis could be that there is no difference, or your working hypothesis would be that there's no difference between the means of your groups, even if you kind of expect there might be. So you're trying to provide evidence using statistics that might lead us to reject our null hypothesis in favor of the alternative. So we saw null or normal distributions. For those of you in class, we saw this the other day in an example where we have these kind of bell-shaped curves, as you see to the right here. So characteristics of our bell curves or our normal distributions is that they're symmetrical around the mean. So the peak of our curves is the mean. Data is symmetrical around that mean. You'll see more density in the center of each of the curves than in the tails. So out here are the tails. In the center is where most of our population will fall. And these distributions are defined by a couple of parameters. First is the mean. Second is the standard deviation. And we'll talk about that in just a minute here. But most of the area that falls under the curve is within one standard deviation of the mean, and that's denoted down here. So we see standard deviation, one standard deviation going out from our mean. So here's our mean. One standard deviation is the area between these two bars, and most, or 68%, of the area of the curve falls within one standard deviation of that mean. And 95% of the area falls within two standard deviations of the mean. You'll also have to understand a little bit about variance for our lab today. So this is a measure of how spread out our data points are from the mean. So how wide is our distribution? And this is defined as the sum of the squared distances of each term in the distribution from the mean divided by the number of terms in the distribution minus 1. Right? Big mouthful. And here is our formula for variance here. And some instructions on how to calculate variance. Good news for you if this looks a little bit frightening to some of you. Excel can do this for us using some handy-dandy functions, and you learned a little bit about functions in Excel. We're going to expand your knowledge of those functions today. So today, when you look at some data for finches, you'll be asked to find the variance in data sets, and Excel will do this for you using this equal VAR function, which means variance. So it'll be pretty simple to calculate variance. Standard deviation is another measure of how spread out numbers of a data set are, so it's related to variance. It's simply the square root of the variance. If you compare the formula here, this formula to our variance formula, variance is simply standard deviation squared, or in other words, standard deviation is the square root of variance. So take-home message here, low standard deviations or low variance mean that numbers in our data set are going to be clustered close together. There's not going to be a lot of spread. We're going to have a high peak in our normal distribution curve and not a lot of individuals out in those tails. Whereas data sets that have high standard deviations will mean that the numbers in the data set are quite spread out over a much larger range. So to calculate standard deviation, there's another handy Excel function, equal STDEV. Just a couple other things you'll need to know. You'll be asked to run a t-test. And t-test helps us to evaluate the means of two groups and assess whether they're significantly different from one another. So t-tests take into account variance, or the spread of the data. When you run your t-test, you'll be asked to assess whether you're dealing with paired or unpaired data. So an unpaired t-test you'll use if the data are not related to each other. So by this, if you're dealing with two entirely different populations of individuals, say individuals in the morning lab and those in an evening lab, those people are not related to one another. So you would use an unpaired t-test. If you're comparing the amount of weight lifted by the football team and the baseball team, again, those players are not related to one another. They're different groups of people, so you'd use unpaired. Conversely, you'd use a paired t-test if there is a relationship in the data. So if you were comparing the scores of this particular lab, so your lab, before and after you study for the exam, the same group of students are taking that exam before and after. So you're dealing with the same population. So there's pairing in that data set. Or if you're comparing the amount of weight lifted at the amount of weight that football players are able to lift at the beginning of the season and the end of the season, you're dealing with that same population. So you'd use paired in that case as well. So consider this example. So say you're studying a group of house wrens, a songbird, and you're comparing the number of songs sung by birds living in yards and forests. So you have a population of yard birds, population of forest birds. Would you use a paired or an unpaired test? Think about that. Pause the video. Another example here. If you're comparing the number of songs sung by birds before and after the introduction of a predator, so in this case you'd be dealing with the population of the birds living in the same area, just before and after you introduce a predator to that area. Would you use paired or unpaired? If you said unpaired for the first example, the yard and forest birds, you're correct. And if you said paired for the predator example, you're correct there. All right, the last thing we need to understand is the p-values. So this is kind of the magic number that we get once we run a t-test. And for us, anything below 0.05 means that we can reject our null hypothesis in favor of the alternative. So if the p-value is below 0.05, this is strong evidence against the null hypothesis, so we reject the null. So what we're effectively saying is that the result we're getting is going to be due to chance less than 5% of the time, which is pretty good. So we can conclude that there's a significant difference. So for example, say you get a p-value of 0.023, you'd be saying that there's only a 2.3% probability that you have mistakenly rejected the null. So you have pretty strong probability there. Conversely, if you have a high p-value, if it's above that 0.05 threshold, you accept the null hypothesis because you don't have strong enough evidence against the null.